In the previous class we are discussing about input-output organization, where we have come up with what is the role of an input-output interface in an input-output organization and asynchronous transfer, where we have come up across the data transfer between the CPU and the input-output devices. Now we are going to talk about different modes of transfer. What are the different modes in which the input-output devices can communicate with the CPU? So coming to the modes of transfer, as we already know, the information in a computer is transmitted in a binary form. So whenever the input output devices wants to transfer the information between the CPU, when information is transmitted between the CPU and the input output devices, that is actually whenever, for example, if you take a keyboard, the input or the information from the keyboard is first stored in the memory before it is giving as an input to the CPU. Similarly, whenever a result is available as an output to be given as to the output device, that is being stored in the memory, so that the information from the memory unit is transmitted to the output device. So the binary information that is received from an external device is usually stored in the memory unit of a computer, and the information that is transferred from the CPU to the external device is originated from the memory unit. So the CPU acts as an intermediary in transferring the information between the memory unit of a computer and the input output devices. So there are basically different modes in which this transformation can take place. There are actually, it can be done in 3 modes. So it can be done, the data transfer can be done in 3 modes. One is the programmed I/O, interrupt initiated I/O and direct memory access. So we will see each and every mode in detail. Next, coming to the programmed I/O, programmed input output. So in case of a programmed I/O, it is used to transfer the data between the input output device and the memory unit of a computer with the intervention of the CPU. So the CPU acts as an intermediary in transferring the data between the input output devices as well as the memory unit of a computer. And this, in case of a programmed I/O, as the name implies, it is done with the help of a program. So that's why we call it as a programmed I/O. Next, we'll see the diagram how this programmed I/O can be implemented. So if you see here, there is a CPU and there is an input output interface and the input output devices. So we already previously we have seen what is the role of an input output interface of a computer. So it acts as an intermediary for the transfer of information from the CPU and the input output devices. So there exists an intermediary, which is an interface to transfer the information between the I/O device and the CPU. For example, this figure will explain you how the data transfer will take place from the input output device between the input output device and the CPU. So consider an input device. Consider a keyboard has an information that has to be transferred to the memory unit through the intervention of the CPU. In that case, the input output device, which is a keyboard, it places the information onto the input output bus. And once the information is placed onto the bus, it enables the data valid signal. So whenever the data valid signal is enabled, the interface unit of the computer or the interface unit of the input output device will transfer the data from the input output bus into one of its register, which is called as a data register. And whenever the data register has an information, then there is a register called as a status register present in the interface unit of the input output device, which has a flag bit F. And when this flag bit is set to 1, it indicates that there is a data that is present in the data register. And if the flag bit is 0, it means that the data register does not have any information. So whenever the input output interface transfers the information from the bus into the data register, it automatically sets the flag bit to 1. So when flag bit is 1, the interface will enable the data accepted line. So once the flag bit is set to 1, automatically the interface will enable the data accepted line. This is nothing but an acknowledgement to the device, input device, that the particular data has been accepted by the interface unit. And similarly, whenever there is an information present in the data register, that has to be transferred to the CPU, that is done by means of a data bus. So the information which is present in the data register of an interface is transmitted to the CPU through a data bus. So this is how the information from the keyboard will be transferred through the CPU it will be transferred to the memory unit of a computer with the intervention of the CPU. Similarly, for example, the memory unit has an information or an output that has to be transferred to the output device or a monitor. In that case, the CPU will enable the address bus. It places the address of the output device onto the address bus, and depending upon the type of operation it want to perform, IO read or IO write operation, it enables the corresponding lines and it will transfer the data from the memory unit to the output device. So this is how the normally the communication between the input output devices and the CPU takes place. Next. So the same thing is explained here. The IO device places the data on the data bus and enables the data valid line, and then the data on the input output bus is placed onto the data register of the interface, and the corresponding bit of the flag bit is set to 1. So whenever the corresponding flag bit is set to 1, it will enable the interface unit of the input output interface will enable the data accepted line. So the data will be transferred from the data register to the CPU by placing it on the data bus. So this is from the CPU point of view. For example, consider the information is placed into the data register of the interface. From the CPU point of view, what the CPU is going to do in order to transfer the data from the interface unit to the memory unit of a computer. So there is a flag bit, as I already told you, the flag bit will be set to 1 whenever the information is present in the data register. So when the CPU, what it does is it frequently keeps on checking the flag bit, checking for if the flag bit is 1, it indicates that the information is present in the data register that has to be transferred to the memory unit of a computer. So it keep on checking the flag bit. For example, if flag bit is set to 1, it has an information, so it reads the status register and transfers the data from the data register. And if the operation is not yet completed, it still has the data that need to be transferred. Then it again goes back and read the data register and complete the process. And if the operation is complete, it will continue with the rest of the program. And consider the flag bit is set to 0. There is no data present in the data register. In that case, what the CPU will do is it keeps on going into the loop, continuously checking the flag bit until it gets the flag bit to 1. And consider it may take 1 hour or 2 hours, we do not know when the data will be available in the data register. So what the CPU is doing here is it is keep on looping checking for the flag bit until the data is available, which makes it doesn't make any sense, because the CPU is wasting lot of its time in checking the flag bit. As we already know, the CPU is the main purpose of the CPU is to execute the instructions, thereby increasing the throughput of the computer. But here the CPU is wasting most of its time in checking the flag bits, which is one of the major drawback of programmed IO. So if the flag bit is 1, it reads the data from the data register and transfers the data into the memory unit of a computer. If the flag bit is 0, the CPU again loops and keeps checking continuously until the flag bit is set to 1. So it is the responsibility of the CPU to check the flag bit and not the responsibility of the interface unit. So that is the main drawback. So which goes continuous, the CPU goes continuously busy waiting, not performing any other operation rather than checking the flag bits, which is one of the major drawback of programmed IO. So if we can, the disadvantages of programmed IO is nothing but it is very inefficient approach, because it is the responsibility of CPU to check for the flag bit, and interface unit does not do any checking of the flag bits. So which is inefficient, which affects the performance of the CPU. So we go for the next type of a mode of transfer, which is nothing but a interrupt initiated IO. So in case of an interrupt initiated IO, in order to overcome the drawback of programmed IO, here the CPU is not going to check anything or check the flag bit. It is the responsibility of the interface unit in order to send an interrupt signal if at all it has any information or a data to be transferred to the transferred from the data register. So in this method, an interrupt command is used by the IO device, interrupt device, in order to inform the device or the CPU about the start and end of the transfer. So when the interface unit of a input output interface determines that there is an information that is taken as input from the keyboard that has to be transferred to the memory unit of the computer, which requires a CPU intervention, then it will intimate the CPU to do this with the help of a special signal which is called as an interrupt signal. So interrupt signal is nothing but it is a special signal that requires the intervention of the CPU or attention of the CPU. So when CPU receives such type of an interrupt signal, it will stop doing whatever program it is executing or whatever task it is doing, and it will come to the interrupt service routine of this particular program. It will perform a data transfer, and after completing the task it will go back and it will continue with wherever it has stopped. So in this case the CPU does not check the flag bit, it is the responsibility of the interface to check the flag bit and intimate the CPU with the help of an interrupt signal. So data transfer, next in this case there is one thing which we come across as a priority interrupt. So I am telling you like the interface unit of a computer will send an interrupt signal to the CPU whenever an information or a data is present in the data register that need to be transferred, right? But there are different types of devices present, input output devices present in the computer that requires the intervention of the CPU to perform their task. So many, for example, there is a printer, there is a like monitor, there is a hard disk. So everyone requires the intervention of the CPU. So they can generate the interrupts, right? So data transfer between the CPU and IO devices is initiated by the CPU, but there are number of IO devices that are attached to the computer, and they are also capable of generating the interrupts. So if at all there are more than one interrupt that is received by the CPU, how can the CPU handle the interrupt? Like for example, at the same point of time the keyboard has generated an interrupt, and similarly at the same time the monitor has also generated an interrupt to the CPU. In that case, how the CPU is going to handle that interrupt? That is taken care by means of a priority interrupt. So it has to identify which is the one that has to be serviced first, whether it has to provide service to the keyboard first or to the monitor first. So whenever interrupt signal is generated from more than one device, the priority interrupt system is used to determine which device is serviced first. So what we are going to do with that is, in order to determine which device has to be serviced first, the CPU is going to assign the priorities to the input output devices. So whichever is having the high speed transfer, they are given a high priority, whereas the low speed devices are given the low priority. For example, if you consider magnetic disks, they are given a high priority because the data transfer rate is very high. So like that, depending upon the speed of transfer, the devices are given certain priorities. So the high priority devices are serviced first by the CPU, whereas the low priority devices are serviced next by the CPU. So in case of interrupt initiated IO, we have two types of approaches. One is a software approach and other is a hardware approach. So in case of a software approach, we apply a mechanism which is called as a polling mechanism. In case of a hardware approach, we go for a daisy chaining mechanism as well as a parallel priority interrupt or parallel priority encoder. And polling mechanism and daisy chaining mechanism both are similar. It is a software approach. The polling is implemented as a software approach with the help of a program, whereas the daisy chaining mechanism is similar to a polling mechanism, but it is implemented as a hardware approach. So we will see each approach. The first type is a polling mechanism. So as I already told you, we are going to assign a priorities to the devices so that the CPU will identify which is the high priority device, and that particular high priority device will be serviced first, and then we go for the next high priority device. So if a high priority device generated the interrupt signal, the CPU will execute the interrupt service routine program of that particular high priority device. If the high priority device does not generate the signal, it will check for the next high priority device. So if you see here, 0, 1, 2, 3 are the 4 devices which are given priority, where 0 is given the high priority, where highest number is nothing but your lowest priority. So the first the CPU is going to check whether 0th device has generated the interrupt. If that is not the device which generated the interrupt, then it will check for the next high priority device, which is 1. So if 1 has generated, so for example consider 1 and 2 has generated the interrupts. In that case CPU will first check 0 has not generated the interrupt. In that case it will check 1. So since this is the next high priority device, that will be the interrupt service routine of this particular device will be serviced, and then it will move on with the next high priority device. So here there are two types of addresses present for each and every input output device, which we call it as a VAD, vector address, NVAD, which is a non-vector address. So what is this VAD is nothing but vector address means every interrupt, every input output device interrupts, ISR program, interrupt service routine program will be present that has to be serviced by the CPU, and that program resides in the memory at a certain address of your memory. We call it as interrupt vector address is nothing but the address of that particular device interrupt service routine program where it is being stored in the memory, and non-vector address is nothing but for all the interrupts of all the devices, they will be stored at a single location of the memory. We call it as a non-vector address. So ISR program stored at a fixed address. So all the input output devices ISR programs will be stored at the fixed address in the memory. We call it as a non-vector address. And in some cases each and every input output device will have its own ISR program stored at a certain location of the memory, which we define it using a vector address. So next, coming to the polling disadvantages of a polling approach. So the time taken to find the device that generated the interrupt is greater than executing an interrupt service routine program. So suppose here we have only 4 devices, so it might be easy to identify which device has generated the interrupt. But if we consider larger systems where we have more number of input output devices, in that case the amount of time that will be taken by a CPU to find out which device has generated the interrupt, that will be it will be greater than the time that it takes. For example, it takes only some 2 hours to execute the interrupt service routine, but in some cases to find out which device has generated the interrupt, it may take more than 2 hours. So that is one of the disadvantage of polling mechanism. Next we go to the next type of approach, which is a hardware approach. We call it as a daisy chaining priority approach. This is also similar to a software polling mechanism, but this is done in terms of a hardware where the polling mechanism is implemented with the help of a program. So in case of a daisy chaining priority, which is a hardware approach that is implemented using a hardware, it is here we have multiple devices, input output devices connected in the system and the CPU. So all the devices are connected to the CPU by means of an interrupt request line. So all the devices are connected to the CPU through a interrupt request line, and we also have devices VAD, vector addresses of each and every device. So they are connected in a chain fashion, so that is the reason we call it as a daisy chaining priority. So if you see here, the device 1 is a high priority device, whereas the device 3 is a low priority device. So they are connected in a chain starting from a high priority to the low priority. So what happens is, for example, the device 2 want to interrupt the CPU, then it will enable the interrupt request line. This particular line will be enabled. So whenever the CPU receives finds out this particular line is enabled, then it will send an interrupt acknowledgement signal. So it will enable this interrupt acknowledgement signal so that it will go first to the device 1. So since this is not the device that has generated the interrupt, so what device 1 will do is it will forward that particular interrupt acknowledgement. So this PI, PO is nothing but priority input and priority output. So the interrupt acknowledgement signal will be first sent to device 1 through priority interrupt. So if device 1 is not the device which generated the interrupt, it will send the same interrupt acknowledgement message to the next high priority device, which is device 2, through the priority output. So this through P0, PO to P1, it will be P0 to P1, PI. So the particular interrupt acknowledgement will receive the device 2. So since this is the device which enables the interrupt request line, it will place its VAD, vector address of that particular interrupt service routine of device 2 onto the bus, so that the CPU will receive that particular VAD address and then it will go to that particular address of the memory and execute the interrupt service routine. This is how it handles the interrupt in case only one device sends an interrupt. But consider there are more than one devices which enables the interrupt request line. Consider device 2 and device 3, both of them at the same time has generated the interrupt request. In that case, the CPU will send an interrupt acknowledgement to device 1. Since this is not the device which has sent the interrupt, it will forward this to the next device through the PI. So device 2 is the highest next high priority device. So this will automatically send the VAD address onto the bus so that the CPU will handle the next high priority device request. So next it will again send an interrupt acknowledgement, then it will be forwarded to device 3 so that device 3 will place the VAD address onto the bus so that will be serviced next. So this is how the CPU is going to service the interrupt service routines if more than one device sends an interrupt request. So this is how daisy chaining priority mechanism works. Next, coming to the disadvantages of daisy chaining priority mechanism. So the same thing, the same disadvantage which applies to a polling mechanism, here also the time taken for the CPU to find out which device has sent and generated the interrupt will be more than the execution of an interrupt service routine program. So we go for the next type of a hardware approach which is called as a parallel priority interrupt, or we can also call it as a parallel priority encoder. This is also a hardware approach. So this is also one of the approach which is going to find out which device has to be serviced by the CPU if more than one device has generated the interrupt request. So here we have a register called interrupt register and a mask register. So for example, in the interrupt register, for each and every input output device we have an entry. So disk 0, printer 1, reader 2 and keyboard 3. So for each and every device we have an entry present in the interrupt register. So correspondingly there is also an entry for each and every device present in the mask register. So the disk 0, 1 for printer, 2 for reader and 3 for keyboard. So initially all the entries of the mask registers are 1. So make sure that all the entries of the mask registers are enabled to 1. So what happens is there is a priority encoder which takes a and if you see, whenever there is an interrupt from that particular device, this particular bit will be set to 1 so that this 0th bit and this 0th bit will be given as an input to this AND gate. 1 and 1. So when both are 1s, as per the truth table, the output will be 1. So which means that this is the one, this is the device which has, I0 is the device which has generated the interrupt. So this is how we are going to handle. So for example, there are more than one device which has generated the interrupt. So the disk and the printer, both at a time they have generated the interrupts. So in that case, both the bits will be 1. So automatically the mask register bits are also 1. So both will be 1 1. So I0 and I1 will be 1 1. So in that case, next slide. So if you see the truth table for this, so I0 is a high priority device and I3 is the low priority device. So I0, whenever there is an interrupt from I0, so in that case remaining all are don't care. So irrespective of whether they are 1 or 0, this particular device has to be executed. The interrupt service routine for I0 has to be executed by the CPU. And in the second case, if you see, if I0 has not generated the interrupt, I1 has generated, so that is the next high priority device. In that case, irrespective of this is don't care conditions, we don't care about what is output of I2 and I3, this service routine has to be executed by the CPU. So the output will be this particular device I1. So if I0 and I1 are zeros, they have not generated the interrupt. Next high priority device is I2. So in this case, this is a don't care condition where the ISR routine of this particular device has to be serviced. So similarly for the next one. So if all are zeros, nothing will be executed by the CPU. So this is a truth table. Backslide. So depending upon the truth table, if I0 has generated the interrupt, all these are don't care conditions. So I0 will be the output of this particular table. So the particular y and x values will be the first device 0 0. Since this is 0, 0 0 will be the output of bus buffer. And if you see here, we also have AND gate here. So the IEN represents the interrupt enable. So interrupt enable is always on. So whenever the interrupt enable is on, then only the CPU can receive the interrupt from any device. So it has to be on, so it means it is 1. Similarly, IST will be set to 1 whenever there is an interrupt from any of the devices. So here these two devices are 1 1, so automatically this particular flag interrupt enable interrupt status bit, this particular interrupt status bit is set to 1. So these two are given as inputs. So whenever these are both are 1 1 interrupt enable and interrupt status bit, then it will interrupt the CPU. So whenever it interrupts the CPU, it sends an interrupt signal to the CPU will send an interrupt acknowledgement signal, and that is also a 1, that is given as an input to other AND gate. Along with this, the interrupt IST bit is also given as input, as well as IEN bit is also given as input. So whenever it receives an acknowledgement, this bit will also be 1. In that case, it will enable this particular bus buffer, where this particular output 0 0 will be given as an output. So the vector address of this particular disk 0 will be given as an output by the CPU to the CPU, so that the CPU will execute the interrupt service routine of that particular disk, since this is a high priority device when we consider the outputs of disk and printer. So this is how the parallel priority interrupt or a parallel priority encoder mechanism works in order to handle an interrupt request from more than one device by the CPU. So the interrupt register has 4 devices with priorities 0, 1, 2 and 3, and the mask register has 4 fields, 1 for each device. Assumes initially all the bits of the mask registers are 1s. So the AND gate receives the information from the interrupt register and the mask register. So this is how the parallel priority interrupt works. Next we are going to talk about direct memory access. So direct memory access is nothing but we have disadvantages in the previous approaches which leads to a direct memory access. If we see the previous approaches, the information from the to and from the input output devices has to be taken care with the intervention of the CPU. So here we are wasting more amount of CPU time checking for the bits or determining which device has generated the interrupt. So we are affecting the throughput of the CPU. So rather than intervention of the CPU, we are going for the other concept which is called as the direct memory access, where the information between the memory unit of a computer and the input output devices will take place without the intervention of the CPU. So which is nothing but the direct memory access, DMA, using a concept of DMA. So the problems of programmed IO and interrupt initiate IO can be overcome by implementing the concept of DMA. So DMA is nothing but it is a mechanism or a method that allows an input output devices to send or receive the information or data from the main memory bypassing the CPU to speed up the memory operations, which means we are going to perform the sending and receiving of information between the memory unit and input output devices of a computer without the intervention of CPU. So during the DMA transfer, there is no intervention of the CPU is just idle, it will not do any operation or any type of data transfer. So that is actually done by means of a controller of a DMA, which is called as a DMA controller. So this is a diagram which explains you how a direct memory access works without the intervention of the CPU. So here the main role in the DMA is the role of a DMA controller. So irrespective, without using a CPU, here we are using a DMA controller that is responsible for handling or performing a data transfer between the memory unit of a computer as well as the input output devices. So in this case, DMA controller, so whenever there is an information that has to be transferred from the input output device to the memory unit of a computer, the interface circuit of that particular peripheral device will send a request called DMA request. So the DMA request will be sent by that particular interface unit of a peripheral device to the DMA controller. So whenever it has an information or a data that has to be transferred to the memory unit of a computer. So whenever a DMA controller receives a DMA request, it will generate a request called BR request, bus grant request. So this DMA controller will send a bus grant request to the particular CPU. So it is, this bus grant request is nothing but the DMA controller is requesting the access of a bus in order to transfer the data from the DMA controller, from the input output device to the memory. So that is, so it will send a bus grant request to the CPU. So upon receiving the bus grant request, the CPU will generate a signal bus request. So the CPU will generate a bus grant signal and will send that particular signal back to the DMA controller. So the bus grant signal is nothing but whenever the CPU is not going to have an access of the bus. Bus means it has three lines: data line, address line and control line. Control line is nothing but read and write outputs. So whenever the bus request is sent to the CPU will does not have any control of the bus. It is giving its control of the bus to the DMA controller in order to transfer the information from the peripheral device to the memory. So it will send a bus grant signal so that it will inactivate the control line, data line and address line of the bus and giving the access of the bus to the DMA controller. So whenever the DMA controller receives the bus grant signal from the CPU, it will send a DMA acknowledgement. So the acknowledgement to the peripheral device. So whenever a DMA acknowledgement is received by the input output peripheral device or the interface unit of a peripheral device, it means that the DMA controller is ready for data transfer. So in that case, through the address, it places the address of the memory onto the bus and data onto the data bus, and it enables the read or write depending upon the read or a write operation that peripheral device wants to perform, and using this the information will be transferred to the memory unit of the computer. So it will be the information will be transferred from the IO device through a DMA to the memory unit. So once the entire process is completed, once the information from the peripheral device is transferred completely to the memory unit, the next thing is it will send an interrupt. So next, once the data transfer is completed, the DMA controller will again send an interrupt signal to the CPU, and this interrupt signal means that the DMA controller is done with the data transfer operation. You can take the control back. So in that case, the CPU will now invalidate the address control data line of this particular DMA controller, and it will enable the lines. So that now the data transfer has been completed, the control of the bus is given back to the CPU. So this is how a DMA transfer works. So the DMA is whole and sole responsible for transferring the information between the peripheral device and the memory without the intervention of the CPU. But before the actual data transfer takes place, it requests the CPU for the control of the bus, it gains the access of the bus, it performs the transfer of information through the bus, and once the transfer is completed, it gives the control back to the CPU by using an interrupt signal. Next. So when bus grant signal is equal to 1, it specifies that the DMA controller has a bus grant. So when bus grant is equal to 0, it specifies that the CPU has bus grant. So whenever a CPU gives the control of the bus to the DMA controller, it makes bus grant signal to 1. So now the DMA controller has a control of the bus where it can transfer the information, and once the transfer of information is done by the DMA controller, it sends an interrupt signal to the CPU so that it makes the bus grant to 0. So when bus grant is equal to 0, now the CPU has the control of the bus. So this is how it specifies by means of BG signal, bus grant signal, making 1 or 0 depending upon who is having the control of the bus. So once the DMA transfers the entire data, it sends an interrupt signal to the CPU. CPU will then enable its address line, data line and control line and disables the bus grant signal. It makes the bus grant BG to 0. So DMA control registers. So in a DMA controller, whenever the information is being transmitted by a DMA controller, it has 3 types of registers that are present in the DMA controller. One is an address register, word count register and control register. So address register, it specifies the address or the desired location in the memory where the particular information will be read or written by the input output device. So it contains the address to specify the desired location in the memory, to which location of the memory the particular DMA controller is transferring the data, whether it is a read operation or a write operation, whatever it is, to which address it is being done, that is specified by an address register. Word count register contains the number of words to be transferred. How many words, how much amount of information is being transmitted by the DMA controller, that is specified by means of a word count register. Next comes a control register. It specifies the transfer mode, whether a controller is performing a read operation into the memory or a write operation. So that particular control information is specified in the control register of a DMA controller. Next coming to the data transfer using DMA. So we are transferring the data between the input output devices and the memory unit of a computer, but there are two ways to perform a data transfer between by the DMA controller. The first method is using a burst transfer mode and the second method is using a cycle stealing mode. So what happens in the burst transfer mode is that we are going to transfer a burst of data, or a continuous blocks of words is transferred in a continuous burst. So at a time we are going to transfer multiple words of data from the input output device to the memory unit of a computer using a burst transfer mode. So a block or a collection of memory words is transferred in a continuous burst. So here, and why do we require this type of a transfer? It is for a high speed devices. For example, if you take a magnetic disk or a hard disk, so in those type of situations you require the data transfer to be very much fast. So in those type of devices, the burst transfer mode will apply. Next type of a mode is a cycle stealing mode. In case of a cycle stealing mode, it allows a DMA controller to transfer one word at a time. So here we are going to transfer only one or two words at a time, because in this case, so after each and every word it transferred from the input output devices to the memory, we are again going to give the bus grant back to the CPU, and then again for the next word we have to get the access of the bus and then transfer the next word. So for each and every word of transfer of the word, we require the access of the bus by the CPU. So this allows a DMA controller to transfer one data word at a time, after which it must return the control of the bus to the CPU. So for each and every word of information that has to be transferred from the input output devices to the memory, we require the access of the bus. So once we send one word to the memory, then we again give the control of the bus back to the CPU, and then for the next word we again request the access of the bus. So like this, for each and every word that has to be transferred, we are going to access the bus. So that is called as the cycle stealing mode. So these are the two ways in which the data transfer can take place in case of a direct memory access mechanism.